When dealing with a remote panel feed for a new house, several grounding considerations must be addressed to ensure compliance with the National Electrical Code and maintain electrical safety. The specific scenario involves an existing 400 amp single-phase service at a pole building feeding a new house 100 feet away with a 200 amp service. Two potential options for handling the grounding conductor associated with the feeder to the house and a separate generator feed are presented. Let's analyze each option. Option 1 involves running the grounding conductor to the service disconnect. The advantages are: firstly, it meets the requirements of the National Electrical Code section 250.32. (2) By providing a grounding conductor for the service entrance. Secondly, it eliminates the potential for a ground fault in the generator feed from affecting the rest of the electrical system. The disadvantages are: firstly, it may be more labor intensive, as it may require removing the bonding bar separating conductors and rerunning the grounding conductor. Secondly, it may not be compatible with the existing wiring if the system is not already configured for separate grounded and grounding conductors. Option 2 involves not landing the grounding conductor. The advantages are: firstly, it allows the use of the generator in its currently bonded configuration. Secondly, it is quicker and easier to implement. The disadvantages are: firstly, it violates the National Electrical Code section 250.32. (2) Which requires that a grounding conductor be installed for service entrances. Secondly, a ground fault in the generator feed could result in a dangerous voltage being present on exposed metal surfaces in the house. Considering the National Electrical Code requirements and safety implications, the recommended option is option 1, which is to run the grounding conductor to the service disconnect. While it may require more effort, it ensures compliance with the National Electrical Code and provides a safer electrical system. Here are some additional considerations. Firstly, if the existing wiring in the house is not compatible with separate grounded and grounding conductors, it may be necessary to upgrade the wiring or use a different approach. Secondly, the size of the grounding conductor should be at least equal to the size of the grounded conductor for the service. In this case, it should be 4/0 aluminum. Thirdly, a ground rod should still be installed at the house for additional grounding protection. Fourthly, the generator connection should be properly sized and protected according to the manufacturer's specifications and local codes. Now, let's delve deeper into the requirements of the National Electrical Code section 250.32. Be related to grounding systems for separate buildings or structures. This section provides detailed guidelines for ensuring electrical safety and proper grounding when supplying power to a detached building or structure from a main service. The goal is to minimize the risk of electric shock, fire, and equipment damage. According to the National Electrical Code section 250.32, there are two primary methods for establishing a grounding system at a separate building or structure. The first method involves running a grounding conductor from the main service to the separate building or structure. This grounding conductor must be sized appropriately based on the size of the ungrounded conductors supplying the building or structure, as specified in National Electrical Code section 250.122. The grounding conductor serves as a low impedance path for fault current to return to the source, allowing overcurrent protective devices to trip and clear the fault. The second method involves establishing a local grounding electrode system at the separate building or structure. This grounding electrode system must consist of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes. The grounding electrodes must be bonded together to form a single grounding electrode system. The purpose of the local grounding electrode system is to provide a path for fault current to ground in the event of a ground fault at the separate building or structure. In addition to the grounding electrode system, a bonding jumper must be installed between the grounding electrode system and the metal enclosure of the service equipment to the separate building or structure. The bonding jumper ensures that the metal enclosure is at the same potential as the grounding electrode system, minimizing the risk of electric shock. When a grounding conductor is run from the main service to the separate building or structure, it must be connected to the grounding electrode system at the separate building or structure. This connection is typically made at the service equipment enclosure. The grounding conductor and the grounding electrode system work together to provide a comprehensive grounding system for the separate building or structure. It is important to note that the National Electrical Code Section 250.32 B also addresses the requirements for grounding systems in agricultural buildings. Agricultural buildings often have unique grounding challenges due to the presence of livestock and the potential for corrosive environments. The National Electrical Code requires that agricultural buildings have an equipotential plane to minimize voltage differences in livestock areas. The equipotential plane is typically constructed of concrete and reinforced with wire mesh or rebar. The wire mesh or rebar is bonded to the grounding electrode system to create a low impedance path for fault current to ground. In a specific scenario, since a separate generator feed is being installed, it is crucial to ensure that the generator is properly grounded. The National Electrical Code requires that generators be grounded in accordance with National Electrical Code Section 250.34. This section provides detailed guidelines for grounding portable and stationary generators. For portable generators, the grounding requirements depend on whether the generator is used to supply equipment connected by cord and plug or whether it is used to supply a building or structure. If the portable generator is used to supply equipment connected by cord and plug, it is not required to be grounded if it meets certain conditions. These conditions include that the generator only supplies equipment located on the generator itself or on the vehicle or structure on which the generator is mounted, and that the non-current carrying metal parts of the equipment are bonded together. If the portable generator is used to supply a building or structure, it must be grounded in accordance with National Electrical Code Section 250.32. B. As previously discussed. For stationary generators, the grounding requirements are similar to those for portable generators used to supply a building or structure. The stationary generator must be grounded in accordance with National Electrical Code Section 250.32. B. In addition to the grounding requirements, it is important to ensure that the generator is properly sized for the load it will be supplying. The generator must be capable of supplying the total connected load of the building or structure, including lighting, appliances, and equipment. It is also important to consider the starting current of motors and other inductive loads when sizing the generator. The generator must be able to handle the inrush current of these loads without stalling or damaging the generator. When installing a generator, it is important to follow all applicable codes and regulations. This includes obtaining the necessary permits and inspections from the local authorities. It is also important to consult with a qualified electrician to ensure that the generator is installed safely and correctly. Now, let's discuss the sizing of the grounding conductor. The size of the grounding conductor is determined by the size of the ungrounded conductor supplying the building or structure, as specified in National Electrical Code Section 250.122. The National Electrical Code provides a table that lists the minimum size of the grounding conductor based on the size of the ungrounded conductors. For example, if the ungrounded conductors are 4/0 aluminum, the minimum size of the grounding conductor is 2/0 aluminum. It is important to note that the grounding conductor must be installed in the same raceway or cable as the ungrounded conductors. This ensures that the grounding conductor is protected from physical damage and that it provides a low impedance path for fault current to return to the source. In addition to the grounding conductor, a bonding jumper must be installed between the grounding electrode system and the metal enclosure of the service equipment at the separate building or structure. The bonding jumper ensures that the metal enclosure is at the same potential as the grounding electrode system, minimizing the risk of electric shock. The size of the bonding jumper is determined by the size of the ungrounded conductors supplying the building or structure, as specified in National Electrical Code Section 250.102. The National Electrical Code provides a table that lists the minimum size of the bonding jumper based on the size of the ungrounded conductors. For example, if the ungrounded conductors are 4/0 aluminum, the minimum size of the bonding jumper is number 6 copper. It is important to note that the bonding jumper must be installed in a manner that provides a low impedance path for fault current to return to the source. This means that the bonding jumper must be securely connected to the grounding electrode system and the metal enclosure of the service equipment. It is also important to ensure that the bonding jumper is protected from physical damage. Now let's discuss the installation of ground rods. Ground rods are a common type of grounding electrode used in grounding electrode systems. Ground rods are typically made of copper-clad steel or stainless steel. They are driven into the ground to provide a path for fault current to ground. The National Electrical Code requires that ground rods be at least 8 feet long and that they be driven into the ground to a depth of at least 8 feet. The National Electrical Code also requires that ground rods be spaced at least 6 feet apart. This spacing is intended to prevent the ground rods from interfering with each other and to ensure that they provide a low impedance path for fault current to ground. When installing ground rods, it is important to avoid underground utilities. Before driving ground rods, it is important to contact the local utility companies to locate any underground utilities in the area. This will help to prevent damage to the utilities and to avoid the risk of electric shock. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates and underground metallic water pipes. Ground plates are typically made of copper or galvanized steel. They are buried in the ground to provide a path for fault current to ground. Underground metallic water pipes can also be used as grounding electrodes, but they must meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. It is important to note that plastic water pipes cannot be used as grounding electrodes. In summary, when installing a remote panel feed for a new house, it is crucial to follow all applicable codes and regulations. This includes properly grounding the system in accordance with National Electrical Code Section 250.32. B and National Electrical Code Section 250.34. Sizing the grounding conductor and bonding jumper correctly, and installing ground rods or other grounding electrodes properly. By following these guidelines, you can ensure that the electrical system is safe and reliable. Let's talk more about aluminum wire. When working with aluminum conductors, it's crucial to understand their properties and how they differ from copper conductors. Aluminum is a lighter and more cost-effective alternative to copper, but it has some unique characteristics that require special attention during installation and termination. Firstly, aluminum has a higher coefficient of thermal expansion than copper. This means that aluminum expands and contracts more with changes in temperature. When aluminum conductors are installed in electrical connections, this expansion and contraction can cause the connections to loosen over time, leading to increased resistance and potential overheating. To mitigate this issue, it is essential to use connectors and terminals that are specifically designed for use with aluminum conductors. These connectors are typically made of aluminum or have a tin plating to prevent corrosion. They also have a larger contact surface area to distribute the current flow and reduce the risk of overheating. Secondly, aluminum forms an oxide layer on its surface when exposed to air. This oxide layer is non-conductive and can increase the resistance of electrical connections. To overcome this issue, it is necessary to use an antioxidant compound when making connections with aluminum conductors. Antioxidant compounds help to break down the oxide layer and create a gas-tight connection. They also help to prevent the formation of new oxide layers. Thirdly, aluminum is more susceptible to corrosion than copper. When aluminum conductors are exposed to moisture or corrosive environments, they can corrode, leading to increased resistance and potential failure. To prevent corrosion, it is important to protect aluminum conductors from moisture and corrosive elements. This can be achieved by using weatherproof enclosures, applying corrosion-inhibiting compounds, and ensuring that the conductors are properly insulated. When terminating aluminum conductors, it is essential to follow the manufacturer's instructions carefully. The conductors should be stripped to the correct length and inserted fully into the connector or terminal. The connector or terminal should be tightened to the specified torque using a calibrated torque wrench. Over-tightening can damage the conductor, while under-tightening can lead to loose connections. It is also important to inspect aluminum connections periodically to ensure that they are still tight and free from corrosion. If any loose connections or signs of corrosion are found, the connections should be retightened or replaced as needed. When working with aluminum conductors, it is important to be aware of the National Electrical Code requirements. The National Electrical Code provides specific guidelines for the installation and termination of aluminum conductors, including conductor sizing, ampacity, and termination methods. By following these guidelines, you can ensure that the electrical system is safe and compliant. In addition to the above considerations, it is also important to consider the type of aluminum conductor being used. There are several different types of aluminum conductors available, each with its own unique properties and applications. For example, aluminum alloy conductors have higher strength and conductivity than pure aluminum conductors. Compact stranded aluminum conductors have a smaller diameter than conventional stranded aluminum conductors, making them easier to install in tight spaces. When selecting aluminum conductors, it is important to consider the specific requirements of the application, including the ampacity, voltage drop, and environmental conditions. Now let's discuss some common mistakes to avoid when working with aluminum conductors. Firstly, using the wrong type of connector or terminal. As mentioned earlier, it is essential to use connectors and terminals that are specifically designed for use with aluminum conductors. Using connectors that are not designed for aluminum can lead to loose connections, overheating, and potential failure. Secondly, failing to use an antioxidant compound. Antioxidant compounds are essential for breaking down the oxide layer on aluminum conductors and creating a gas-tight connection. Failing to use an antioxidant compound can lead to increased resistance and potential overheating. Thirdly, over-tightening or under-tightening connections. Over-tightening can damage the conductor, while under-tightening can lead to loose connections. It is important to use a calibrated torque wrench to tighten connections to the specified torque. Fourthly, neglecting to inspect connections periodically. Aluminum connections should be inspected periodically to ensure that they are still tight and free from corrosion. Neglecting to inspect connections can lead to loose connections, overheating, and potential failure. Fifthly, mixing aluminum and copper conductors in the same connection. Aluminum and copper are dissimilar metals that can corrode when they come into contact with each other. Mixing aluminum and copper conductors in the same connection can lead to corrosion, increased resistance, and potential failure. In conclusion, working with aluminum conductors requires special attention and care. By understanding the properties of aluminum, following the National Electrical Code requirements, and avoiding common mistakes, you can ensure that the electrical system is safe, reliable, and compliant.